Hello everybody. In this video we will be covering one of the sections in chapter 3 of our textbook entitled Matter and Energy. In this video we'll be covering the first section of chapter 3 that is all about matter. So everything that you can see, touch, smell, or taste in your room is made out of matter. In addition to that, there's some other things inside of your room that you can't really see, smell, or taste that is also made out of matter, like the air in there. It is the job of chemists to study the differences in matter and how it relates, how that relates to the structure of the matter. So again, we're going to try and figure out how matter is going to behave by examining what the matter is actually made of at a really, really small level. So matter is defined as anything that occupies space and has mass. So by occupies space, that means that it has some volume, and we've seen that mass is a quantity that's going to be related to the weight, but isn't exactly the same. Even though it appears to be smooth and continuous, matter is actually composed of a lot of tiny pieces we call atoms and molecules. Okay, so even though this appears to be all one thing, there are actually a bunch of really tiny pieces that are comprising all of it. So atoms are the tiny particles that make up all of matter. And when they start to join together into discrete little units, we call those molecules. Okay, so we start with a set of atoms. We'll see there's only so many different types of atoms, and then they start to bind together to form these molecules through a process we call chemical bonding. And all the different types of molecules you can make then are what allow us to have all the different types of matter that we see in our world. So matter has what we call a physical state, and it can be classified as either a solid, a liquid, or a gas based on what properties it exhibits. You may have also heard of a state of matter called plasma that does exist. But for this class, we're just going to restrict ourselves to talking about solid, liquid, or gas. So the properties that we're interested in are going to be whether or not it retains its shape, whether or not it has a fixed volume, whether or not it's compressible, meaning it can be like pressed together by a piston or something and have its volume lowered, and whether or not it exhibits flow. So a solid has a fixed shape, it has a fixed volume, you're not going to be able to compress it in a piston, and it doesn't flow, right? And you might think, well, something like sand is a solid, but it can flow or be poured from one container to another, but that's not actually true flow. So that's just what happens when you break it up into really small pieces. A liquid does have an indefinite shape, right? If you have a container that you put some water in and you pour it into a different container of a different shape, the liquid is going to fill up the bottom of that container and take on the shape of it. It does have a fixed volume though, right? If you take a liter of water and you pour it into another container, you're still only going to have a liter. It is not compressible, but it does exhibit flow. Right, and we use this actually to make all of our hydraulic machinery and stuff, right? We can get it to flow through a tube and into a cylinder, but it's not going to be compressible, so it's going to push on that cylinder in a very predictable way. And then we have gases. So gases, they don't have a set shape, right? They'll just change to be the shape of whatever container they're in, and they don't even have a set volume. Okay, if you had a chamber and you pulled out a whole bunch of pulled all the air out of it and had a vacuum, right, and then you went to add air back into it, that air is just going to expand until it fills the entirety of the inside of it, right? And spread out evenly. So it has no set volume. It is compressible, okay? You can take, for instance, like a syringe or something, you can close off one end and you can push on the air that would be in there, and you'll be able to get it to compress some. And the pressure inside the syringe will go up, right? And of course, it does flow, right? We can see gases flowing through tubes all over the place in our regular lives. So the atoms and molecules have different structures in solids, liquid, and gases, and that's what leads them to have these different properties. So if we think about how we're breaking this down, now we have matter, we have solid, we have liquid, and we have gas. And we're going to talk about how the molecules that make up these different states, how they are behaving a little bit differently from one another in order to give them the properties that we see. The particles in a solid are closely packed together, and they're in a fixed position, okay? They may vibrate a little bit, but they're not moving around freely. It's this close packing of the particles that results in solids being incompressible, okay? So they're already close together. You can't push them closer together. The inability of the particles to move around results in solids retaining their shape and volume when placed in a new container and prevents the particles from flowing. Some solids have their particles arranged in an orderly geometric pattern. Okay, we call these crystalline solids. So here would be a picture of that, right? Each one is very orderly. It's almost like you're stacking cannonballs here, right? You're just packing them in as tightly as you possibly can, all right? There are many different patterns that can happen, but you're going to see like a regular order to it, almost as if they were stacked up by an actual human being or something like that. And this is what forms what we call the crystalline solid. Other solids have particles that do not show a regular geometric pattern over a long range. So we call these amorphous solids. And some examples would be plastic and glass are typically amorphous solids. And basically what you have is a little bit of a jumble, right? You may have certain regions where it's a little bit more orderly like this, but it's not going to extend over long areas. The particles in a liquid are closely packed, but they do now have enough distance between each other that they have some ability to move around each other, and they're not trapped in one fixed position. The close packing results in liquids not being incompressible, just like solids, but the ability of particles to move allows the liquids to take the shape of their container and to flow. However, they don't have enough freedom to escape and expand to fill the container. Okay, so they do still have a fixed volume. They have some liberty to move around each other, but they can't just take off. They're still sort of bound to the bulk of the rest of the material. In the gas state, particles have complete freedom from each other. The particles are constantly flying around, bumping into each other and the container. In the gas state, there's a lot of empty space between the particles, at least on average. So, they may wind up bumping into each other every once in a while, but for the large majority of it, they are very far apart from one another. Because there is a lot of empty space, the particles in a gas, they can get squeezed together. Okay, and that's what makes them compressible. Because the particles are not held in close contact and are moving freely, gases expand and fill, and this is what allows them to take the shape of their container and still enables flow. So here we have an image of our solid from earlier, and we can see that if we push on it, we're not really going to be able to get those atoms any closer together. However, when we have a gas where there's a lot of free space between them, we can continue to push on this cylinder and get these guys closer and closer to one another. So, a big theme that we're going to have in this course is going to be basically taking matter and breaking it down into smaller and smaller boxes until we have a lot of classifications for matter, and we can talk about the properties of those two. So our two big ones here that we're going to start off with is going to be a pure substance. It has a constant composition and it's homogeneous, and we'll talk about what that means. And mixtures, okay? And mixtures are going to be two or more pure substances. They have variable composition, therefore. So, pure substance. All samples are made of the same atom or molecule in the same percentages. All right, so example would be salt. In mixtures, different samples may have components present in different percentages. An example of this would be like salt water, right? I could add a little bit of salt to water and just have a little salty water, or I could just keep adding salt until it was very, very salty. So if we dig a little deeper into the classification of matter by composition, we come to an important conclusion. And that is that matter, being a pure substance, being made of only one kind of atom or molecule, means that all samples of that matter are going to show the same properties. Okay, so every sample of salt is going to be the same as every other sample of salt, given that if it's pure salt. Whereas a matter that is composed of different kinds of pieces, different kinds of pure substances, that makes it a mixture, well, now we're going to have different properties that are going to depend on the composition of that specific mixture, okay? If you have salt water and you add just a little salt, that's going to have different properties than if you added a whole bunch of salt to it, okay? So the ratios between the different components of the mixture are going to change its properties. All right, so we're going to break down pure substances now into two more groups, okay? So the substances which cannot be broken down into simpler substances by chemical reactions, these are called our elements. These are our basic building blocks, are our elements that can't be broken down any further. But what we're going to find is that most substances that we see in our everyday world, okay, are chemical combinations of elements, right? So they're elements that are bound together to each other, and these are what we call compounds, all right? A compound can be broken down into its elements, the elements that make it up, all right? And the properties of a compound are not related to the properties of the elements that compose it, all right? So that's really key now. So even though we have a fixed number of elements, right, with their properties, but we see a whole myriad of different things, that's because once we start to combine them, we can make these compounds that are not necessarily going to resemble at all the elements that compose them. All right, so we've been talking about atoms and molecules. So this is pretty key here. So the smallest piece of an element is an atom. There are subatomic particles, so there's little pieces that make up an atom, but these are no longer an element. Okay, so once we get any smaller than an atom, now we're dealing with something that we can't really identify with any particular element. It will no longer have the properties of that element. The smallest piece of a compound is called a molecule. All right. These molecules are made out of atoms, and all the molecules of a compound are identical. Okay, so a pure compound has all the same molecule inside of it. All right, and each of these molecules has the same number and type of atoms that are arranged in the same way, bound to each other in the exact same way. So the big lesson here is that atoms go with elements. So elements are made out of atoms, and molecules go with compounds. Compounds are made out of molecules. There are 118 known elements, only of about 91 of which are found actually in nature. The others that are made up, the difference here, are man-made. That we make those in like super colliders and stuff like that, where we actually smash atoms together to make bigger ones. And at this point, we may have now actually filled out the periodic table. It's very likely that we have actually found every single element that there is at this point, and that was a fairly recent development, actually. So now you can see why it's so important that we be able to combine these together to make compounds, because there are definitely more than 91 different things that we see in our world, right? And we need all of them. The abundance of any element is the percentage of it that is found in nature. So it's not like there's the same amount of each one of these elements. Some are more abundant than others. For instance, oxygen is the most abundant element, at least by mass, on Earth and in the human body. So there's a lot of oxygen out there. The abundance and form of an element varies in different parts of the environment. Okay, this is really key too. For instance, right now we're concerned about making lithium batteries, and lithium is actually pretty concentrated in some small areas in South America. So if we want that lithium, we have to go there to get it. And every sample, once again, of an element is made up of lots of identical atoms. Okay, so there's a lot of atoms that are going to make up even a small sample of any particular element. So compounds, this is very key. We're going to talk about it a little bit more later, but they're composed of elements in fixed percentages. Okay, for instance, water is always going to be 89% oxygen by mass and 11% hydrogen by mass. Okay, so there's always these fixed ratios between how much mass of each element it contains. There are billions of known compounds. There are really just so many. Some of them are what we call organic, meaning that they derive from like a living source at one point or another, even though they may not be found in living organisms. And then there's also inorganic ones, which are not associated with any kind of living process or anything, right? So if you think about it as a living being, you're actually making a whole bunch of different compounds that make up you, right? And these are pretty much distinct and only found around living creatures, whereas the rest of nature, anything that's not living, has its own chemistry and it produces its own compounds. The same elements can form more than one different compound depending on how they're bound to each other. For instance, both water and hydrogen peroxide contain just hydrogen and oxygen, right? Water is essential for everyday life, and hydrogen peroxide is fairly poisonous. But still, it just depends on your percentages and how they're bound together. All carbohydrates that we eat, everything from pasta to that regular old sugar you put in your coffee, they all just contain carbon, hydrogen, and oxygen. Again, it just has to do with the ratios and how they fit together. So now we're going to break down mixtures a little bit here. So we have two kinds of mixtures. We're going to have our homogeneous mixtures. This is matter that is uniform throughout. So in a homogeneous mixture, every bit that you take out is going to look like every other bit. All right, it's very uniform throughout. It appears to be one thing. Every piece of the sample has identical properties. though another sample with the same components may have different properties. Remember, they're variable, okay? So within a specific sample, a homogeneous sample, every part that we take out of it is going to be the same, but that's not true if we went and grabbed a different kind of sample that may also be homogeneous. Solutions, for instance, are always homogeneous mixtures, and by solutions I mean when you dissolve one thing in another, right? If you dissolve sugar in your coffee, that's a solution. If you dissolve salt in water, that is a solution. The other type of mixture is a heterogeneous one, okay? And this is when the matter is not uniform throughout, okay? The different components of the mixture are concentrated in different regions of the sample. It contains regions with different properties than other regions. Okay, let's go through a little play-by-play now of the difference between pure substances and mixtures. Okay, pure substances. All samples have the same physical and chemical properties. Okay, and we're going to talk a little bit more about what physical and chemical properties are. They have constant composition. All the samples have the same pieces in the same percentages. Okay, water is always 89% oxygen, 11% hydrogen. They're always homogeneous. All right. They separate into components based on their chemical properties. Okay, so we can break down a compound into its elements, but we can't break down the elements any further. All right. And their temperature, this is a key thing for actually testing whether you have a pure substance or not, but the temperature usually stays constant when it's melting or boiling. Okay, so when something starts to melt to when it's all the way completely melted, if it's a pure substance, you'll have a constant temperature. Mixtures. Different samples may show different properties based on the composition that they have, the percentage of the different components. They have variable compositions. Samples made with the same pure substances may have different percentages, right? They may be homogeneous or heterogeneous, okay? They separate into components based on physical properties, okay? We can separate the components of a mixture based on its physical properties, which is very key. It's very key to a lot of chemistry that we're going to do. And when the temperature changes, when it's melting and boiling, because of the composition change. So what you're going to find is that when you have a mixture and say it starts melting, you're going to see a change in temperature from when you first see it start to melt to when it's completely all the way melted. And that's because of the composition change that's occurring. Here's a diagram of our classification so far. So we have matter. We break it down to pure substances and mixtures. Our mixtures can be homogeneous or heterogeneous. The two different pure substances we can have are elements or compounds. In later chapters, we're going to continue to grow this tree and put them into more and more boxes as we go along. Okay, we've talked a lot about the different properties of matter, and now we're going to give ourselves some classifications of different properties. The first one are going to be physical properties. Okay, these are characteristics of matter that can be changed without changing its composition. Okay, so if there can be a change in this property that's not going to affect the composition of it. It's not going to change the elements or the atoms or compounds that it's made out of, then it's a physical property. Chemical properties, however, are characteristics that determine how the composition of matter changes as a result of contact with other matter or influence of energy. Okay, so a chemical property, when it has a change, all right, it is going to affect it at that very basic atomic molecular level. Okay, it's going to change how the atoms that make up the compound or basically the chemical are going to change. All right, how they're going to be bound to each other. So let's look at some examples here. So physical properties, a lot of these are very recognizable by us: mass, volume, density, phase. Is it a solid, liquid, or gas? Magnetism, does it attract a magnet? Melting point, boiling point, odor, taste, texture. And some of them are a little bit more exotic, like specific heat, volatility, solubility, thermal conductivity, ductility, malleability, or electrical conductance. And we're going to talk about all of these as we move through this course. Chemical properties are often a little bit less familiar to us. Okay, so these can include things like acidity, which we've heard of, but it's kind of hard to nail down exactly what that is. We're going to talk more about it later. Basicity, which is basically the opposite of acidity. Causticity, which is basically the way that it can erode away at something else. Okay, so if something is caustic, then it's able to do that. Corrosiveness, reactivity. How readily does it react with another chemical? And the opposite of that is stability. How much does it resist having any kind of chemical change? Inertness, which is kind of the extreme of stability. It doesn't want to change at all. Explosiveness, we know what this is. Flammability or inflammability, they're the same thing. Combustibility, which is a little bit different actually than flammability. Combustibility has to do with will it ignite if we compress it. Oxidizing ability, which we'll also talk about in a little while, and reducing ability. And these are also, again, opposites of each other, okay? If you oxidize something, the opposite of that is reducing it. So let's take a look at an example of a specific thing, okay? So if we have a pure substance, we can talk about its physical properties. For instance, iron is a silvery solid at room temperature with a metallic taste and a smooth texture, okay? It has a specific melting and boiling point that are quite high. It has a very specific density, which is also quite high. It's 8 times the density of water. It can be magnetized. It conducts electricity, but not quite as well as a lot of other metals will. Not as much as, like, say, copper or aluminum. And its iron's ductility and thermal conductivity are about average for a metal. So ductility is its ability to be drawn out into, say, like a wire, and thermal conductivity is its ability to conduct heat. And it requires 0.45 joules of heat to raise its temperature of 1 gram by 1 degree Celsius. So this is a sentence that's going to describe a specific heat capacity. Okay, how much energy do I have to put in to get it to heat up? All right. Let's take a look at some chemical properties of iron. The iron is easily oxidized in moist air to form rust. Okay, a lot of steel things that you see when it's rusting, it's because of the iron content in it. When iron is added to hydrochloric acid, it produces a solution of ferric chloride and hydrogen gas. Okay, so it's reactive in the presence of an acid. Iron in general is more reactive than silver, but less reactive than magnesium. So it has its reactivity in, there's kind of a scale for it. Okay, so let's talk a little bit about mixtures and their chemical properties. So I keep saying that a mixture is going to have different properties based on its composition, but I think an example really helps here. So for instance, brass, we're pretty familiar with this as a metal, and it is a alloy or a mixture of copper and zinc. So depending on what percentage of copper we put in there versus what percentage of zinc we put in there, we see a whole bunch of different properties for brass. Okay, it affects its density, it affects the melting point that it has, it really affects its color. You can go all the way from almost being reddish to being like a whole yellow color. And it also, in particular, affects its tensile strength. Okay, this is its ability to be like pulled apart without snapping. Okay. And so it's like, and it's in psi, pounds per square inch. So this would be like 50,000 psi. And for the different properties that we have, we found reasonable uses for each different kind of brass that we can make. So we've done everything from pennies to doorknobs to car radiator cores to lamp fixtures and even nuts and bolts. A lot of the ones that you see for plumbing are going to be made out of brass. So the key takeaway here is that depending on the percentage of these two components, we can kind of get different kinds of properties. And once we understand how the different percentages, changing the different percentages changes the properties, we can even tailor a material that's going to have the properties that we need for any specific application. All right, let's transition a little bit here and start talking about changes in matter. Okay, we'll start talking about physical changes. So this is changes in the properties of matter that do not affect its composition. Remember that our definition of a physical property is that the changes don't affect their composition. Okay. A couple of examples of this is heating water. It raises its temperature, but it's still going to be water. Okay. And if we look at our diagram over here, the butane lighter really is a good example for both chemical and physical properties. If I push down on the little button right there, I'm going to start to release butane. Okay. There are butane molecules in here as a liquid. When it comes out, it's a gas, but it's still butane. Okay, we haven't changed anything about the way that these atoms that make up butane are connected or anything about them. Another example might be like dissolving sugar in water. Okay, even though the sugar seems to disappear, it can be easily separated back into the sugar water by evaporation. So if we can separate two parts of a mixture, then it's a good that's another indication that we're dealing with a physical property. So chemical changes involve a change in the properties of matter that change its composition. There's typically going to be a chemical reaction. An example is from earlier is the rusting of iron. Another example, if we go back to our butane lighter here, we have butane here, right? But if we actually ignite it and create a fire, we wind up producing CO2 and water. The molecules that are released from this flame are different than the molecules that were inside of the lighter. Another example would be like when silver tarnishes, right? So rusting is iron meets oxygen, but the tarnish on silver has to do with when it comes in contact with sulfur that's in the air. Okay, so here's the big question. How do I know if it's a physical or chemical change? Let's go back over some of our key aspects of this. A physical change results in a different form of the same substance. The kinds of molecules will not change. A chemical change results in one or more completely new substances. The new substances will have different molecules than the original substances. You will observe different physical properties in the new molecules because the new substances have their own physical properties. Okay. It's key to note here that a phase change is a physical change, okay? And we have a couple of different ones here. We have boiling. This is when we have a liquid going to a gas. We have melting. This is a solid going to liquid. We're familiar with these, okay? A little bit more exotic here is subliming. This is when you have a solid going straight to a gas with no liquid intermediate, okay? There aren't a lot of examples of this, but two that you may be familiar with would be like the mothballs that we use in like closets and stuff. That is made out of naphthalene, and it's a little ball, a little solid white ball, and it has a very distinct odor. And that's because the solid white ball is changing directly to a gas, and we never see any liquid in there. Another example you may have seen is dry ice. This is solid carbon dioxide, and when you watch it, you can actually see like vapor coming off of it, but there's never any liquid there, and that's because the solid carbon dioxide is going straight to gaseous carbon dioxide with no liquid intermediary. The next one we have is condensing. This is a gas to a liquid. This happens a lot. Maybe like you see like the sweat on the outside of a cold glass on a hot summer's day. This is gas that was in the air, maybe water vapor, that's converting over to a liquid when it hits that cold glass. Freezing. This is a liquid to a solid. We see this a lot. We're pretty good with that. And the opposite of subliming is deposition, where we have a gas that converts directly over to a solid. There's actually a lot of compounds that will do this, but we don't see it a lot. One example might be like caffeine. Caffeine, you could do this if you had like one of those caffeine pills, 100% caffeine pills. You could actually crush that up, put it into a flask or something like that, heat it up. It would turn into a gas and sublime, and then after you allowed it to cool, it would deposit onto the side as a solid, and we would never see any liquid in that whole process. So the key thing to realize here is that how we're moving them through these different phases is that we are heating and cooling the substance, okay? So this is true when we're at constant pressure like we usually are. I'm going to put that little caveat in there. Under normal circumstances, the pressure inside of our environment doesn't change very much, and under those conditions, we're only going to be seeing phase changes when we heat or cool a substance. And another thing to note here is that evaporation is not actually a simple phase change. It's actually a solution process. It's a little bit more complicated than just boiling. What's actually happening is that the water is going into the air the same way that like sugar gets dissolved into water. It's just kind of weird to think about that, but that's for a different class. Separation of mixtures. Okay, so to separate mixtures, so separate the different components of the mixture out, these are typically gonna be based on the physical properties of the components. Okay, and they're gonna involve a physical change. The different techniques that we have, so we have different techniques for separating for every different physical property. For instance, if we want to separate something based on its boiling point, we have distillation. Okay, we can separate two different states of matter. Say if you have a solid inside of a liquid or even a gas inside of a liquid, we have fancy filtration systems to be able to separate those. The solid and liquid is pretty common. You can kind of picture that, but we even have ones where we can separate like a liquid from a gas or a gas from a liquid. You may have seen this if you ever work and you have seen like an air dryer or something like that. Maybe if you work in like a car shop or something like that, they have that sort of thing. we can separate it based on how well it's going to adhere to a surface. This is a technique called chromatography, and it's a very, very powerful technique that we use in chemistry a lot. A lot of like the testing and stuff that you have, blood testing and various things of that nature, are all based on this technique of chromatography. We can separate things based on their volatility through evaporation. Okay, if I want to reclaim the salt from water, one method might be to decrease the pressure and increase the temperature until all the water evaporates and leaves the salt behind. And then we can separate things based on density. There are two techniques for this. We have centrifugation and decanting. Decanting being kind of a simpler form of centrifugation where we just pour off the top layer of something. So to get kind of an image of how some of these might work, this is like a kind of distillation apparatus you might see in a chemistry lab where we have a mixture of liquids here. We heat that mixture. The vapor comes up. It's enriched in just one of the components of the mixture. It comes up here. It kind of has to make this little turn eventually here. Some pressure is going to push it down here. It's going to enter this cooling jacket here. So the inside of this is jacketed. There's like two tubes here. So the outside tube is filled with water that's running through it to cool it, and the inside tube has that vapor. It cools it down. Eventually it condenses in there to make a liquid, and that will drip down into our receiving flask down here. So at some point, the less volatile component will be concentrated on this side, and the more volatile component will be concentrated on this side, where volatility is its tendency to go into the gas phase. Here's a filtration setup that you might see. You typically are going to have one of these little conical funnels here. You're going to put like a paper filter in there, similar to like maybe like a coffee filter or something like that. And if you have a mixture of a liquid and a solid, you can pour it in there. This stirring rod sometimes helps you to mix this up and get it moving through the filter a little bit better. Also gives you something to kind of pour down to direct the liquid. And then eventually the liquid is going to come down into some sort of receiving flask, like a beaker, and then the solid is going to remain on top. All right, so shifting gears here yet again, we're going to introduce a new law. Remember, we talked about laws in Chapter 1. This one is going to be our law of conservation of mass. It was invented by this fellow right here, the powdery wig guy from the way, way back past, named Antoine Lavoisier. And he said that matter is neither created nor destroyed in a chemical reaction. The total amount of matter present before a chemical reaction is always the same as the total amount after. So this is kind of the consequences of what he's saying here, that we're going to basically have the same amount of mass before and after a chemical reaction. The total mass of all the reactants, the stuff we started with, is going to be equal to the total mass of all the products. So the total amount of matter remains constant in a chemical reaction. So in the end of this process, we're going to have just as much mass of carbon dioxide and water molecules as we did butane molecules going in. Let's put some numbers to this. If we had 58 grams of butane burns and 208 grams of oxygen to form 176 grams of carbon dioxide and 90 grams of water. So here is our starter chemical reaction here. We have our reactants here, butane and oxygen. We have our products here, carbon dioxide and water. We're drawing an arrow to indicate that a chemical reaction has happened. These guys are going to carbon dioxide and water. Let's replace these values from our word problem up here for each one. And then we'll do those summations, and we see that in the beginning here, we started with 266 grams, and at the end, we still had 266 grams. We never lost any mass during the process.